Hello, my name is Nicholas Laraquente, and I'm presenting the work Approximate Unitary K-Designs from Shallow, Low Communication Circuits for Innovations in Theoretical Computer Science 2025. This is joint work with Felix Laditsky at the University of Illinois. I will start by recalling a setting that is probably familiar to the quantum audience, which is that quantum states transform under unitary matrices. For the more computer sciencey, these can be thought of as the analogs of circuits, which might act on a string of input bits and transform it reversibly to a string of output bits. Now, unitaries as a group are compact when acting on a finite dimensional Hilbert space, which means that there is a notion of a Haar or a uniform measure on them. So we can meaningfully talk about a random or average unitary. And often the study of these will be enlightening. There's a review article on Haar measure tools or random unitaries that just came out pretty recently. I'd like, however, to highlight a couple of applications. One of them is in quantum information theory, where random unitaries actually underlie some of the foundational constructions. They're used in what's called decoupling, which is one of the primary arguments for how one can obtain notions like the capacity of a channel to reliably transmit bits over many uses, even if that channel is itself noisy. It was also famously used in resolving the additivity conjecture in 2009. Quantum random unitaries are also now coming up quite frequently in theories connecting computer science ideas to high energy physics and to fundamental physics. So there's a bunch of work now on random unitaries as models of black holes. This is a diagram from one of the more famous papers. Here, this VB here is a unitary that is acting possibly as a black hole would on some qubits that are dropped into it by Alice and Bob. And this paper then studies under what circumstances Bob might be able to recover some of the information that Alice leaked into the black hole. A drawback of random unitaries is that to truly realize them requires exponentially deep quantum circuits or exponentially long time evolution. So some ideas about the computational complexity of the physical world would even suggest that maybe we should not expect to see random unitaries in physics because they are so complex, and therefore to see a random unitary should really take a ridiculously long time. This also limits their use in information and computing because they're not tractable to create in any sort of substantially large dimension. One solution to this problem is to create ensembles of unitaries that appear to be random. So I will call the notion of a quantum channel, which is another notion of a transformation on quantum states. This time it's acting on matrices and it's modeling potentially noisy or potentially processes that include the randomness in them. Now, for quantum channels, there's a particularly strong way of comparing them, known as CP order. And in this comparison, we say that a channel is larger than another, or often than a multiple of another, if the difference is itself completely positive, meaning that this could actually be written as a convex combination of the channels. So I also want to introduce the what I might call a twirl with respect to a measure. which is an integral over the unitary group, this does yield a channel. But the unitary group here is acting k times. So this is kind of like a k-fold twirling with respect to this measure mu. And so it's acting on a system of dimension d to the k, where d is some sort of original dimension, and we're thinking about a k copy setup. A measure mu on the d-dimensional unitary group, UD, is an epsilon approximate multiplicative or relative error k design if it obeys this condition with respect to this completely positive order and the Haar or uniform measure. So we would think of this as saying that the first k statistical moments are nearly equivalent to those of the uniform measure. This is a stronger notion than being close to uniform for the k-fold distance, say, in diamond norm or some other operational notions that come up in quantum info. So this is actually a very strong notion that says that this looks very uniform. And these have a long history. Some years ago, probably around 2006 to 8, there were some papers on the just sort of the concept of these unitary designs and where they might come into quantum information theory. Heading into the 2010s, there were a bunch of papers showing that these could be constructed using tractable circuits. So circuits that are constructed of basic gates and that are polynomial size and that have some locality properties. So a bunch of papers were studying these. And very recently, there was kind of a flurry of papers showing that, in fact, you can make the circuits that produce these linearly deep, and showing that some of the constructions, especially in this parameter k, reach optimality. There are also a bunch of open questions, though. So it was often assumed that if you have m qudits on a one-dimensional line, you would need depth somewhere around m times k to get a design. It was also believed that these require a lot of entanglement because random unitaries are highly entangling. So you couldn't fake having very high entanglement. It was an open problem in one of these earlier papers to construct whether it's even possible to construct relative error k designs in sublinear depth in this sort of number of qudits. And they had shown that you can do this in higher dimension for the norm error, but not for the relative error. Also, of course, they left open of what if the dimension is sort of, or the spatial dimension of a lattice is higher. Can you construct a relative error design with depth that is less than the side length, say, or than the diagonal length? So what if there's not enough circuit depth to move a qudit all the way from one side of the chain to another? Maybe intuitively one would think, okay, that shouldn't be able to act like a random process because random processes move everything everywhere. So here, this brings us to current work. We actually found maybe a different answer from the expectations that, again, recalling this definition of a relative error design, we were able to construct slightly structured random circuits that yield relative error k designs in depth that's actually logarithmic in the qudit number. So this log m is kind of the most interesting part of this equation. The concurrent paper by Schuster and co-authors was able to do this in the same m dependence. They were able to improve the k dependence by one factor. So how did we actually find that this works? Our approach was to actually start by looking at it as a communication problem. So let's say you have two parties. they want to construct a unitary design on their joint system, and they want to do that with minimal bipartite communication. So a basic scheme to do this would be that each of them are going to perform approximate local twirls, sort of try to approximate a design-like ensemble. Then they're going to do some information exchange. And finally, they will again do some local twirls that approximate design ensembles. So what this leads to is that they achieve a relative error epsilon approximate design whenever the amount of communication is at least as large as something that scales with k and this error parameter epsilon. But as you might be able to see, there is no dependence on m, or what we would think of as the original system size. You could also ask, well, are stages of this protocol even entirely necessary? What if they just do the local twirls and then the exchange? And with the modification, instead of having them exchange some qubits at the end, we'd actually have them perform a unitary that's chosen from a design ensemble on some system that overlaps with both after doing their local twirls. And this, again, gets this k and epsilon scaling, no m scaling. They do achieve here a spectral gap with even sort of a stronger dependence that shows that they're starting to move toward a design even faster. So the spectral gap is a norm-based notion. This comes from the Schatten p-norm of a matrix, which is the matrix analog of the vector p-norm and can be defined with respect to a trace. And it naturally induces a channel p-norm, which is a ratio of norms between input and output, and what's called completely bounded strengthening, which even says that this would bound any sort of auxiliary extended system. So the spectral gap between a channel and its fixed point projection, if it has a fixed point projection, is this 2 to 2 norm, essentially, or this distance induced by it. And for a pair of projections, if they have an intersection subspace projection, which they generally would, the subspace angle is actually a special case of this spectral gap. So we had a very detailed analysis of the subspace angle. And in particular, we actually went beyond the Alice and Bob scenario to consider multiple systems, each repeated k-fold, each with some local and some crossing twirls. And so here you see these color-coded local twirls on each of the individual going vertically and the k copies going horizontally. And then this would actually do the crossing twirls or the exchanging operations, which again, we respect the k copy structure, but now are kind of mixing the qubits between these different parties. And what this leads to is actually a very nice subspace angle bound that in terms of the different numbers of qudits that each party contributes to the cross twirl, the k and the sort of local qudit dimension, we end up with sort of a bound that's exponential in the qudits exchanged, inverse exponential, and linear in this k. How we got this? Well, this uses a well-known method based on Schur-Weil duality, in which we can split unitary representations of the symmetric group and the repeated unitary group on the k-fold space. So here, this is actually going to split the Hilbert space into irreducible representations, or irreps. And you see that sort of one kind of irrep is representing permutations. This is this phi of pi. Pi is a permutation. And this psi of u is the representations of the unitary group. Now, by Schur's lemma, any operator that commutes with all the unitary representations actually has a special form in terms of permutation representation. So if we know that something is invariant under the unitary group, it's sort of carrying no unitary group information, we can rewrite it fully in permutation. And more deeply, in the bipartite case, we would actually decompose operators into these and rewrite inner products of operators on the space as inner products of vectors that represent the coefficients of these different permutations. So this is one example. There's sort of a bunch of different ways of doing this for the different quantities we need. And we apply some results of Haar and Harrow in a paper that was actually quite recently released, approximate orthogonality of permutation operators. And this shows some calculations on what these inner products actually come out to. And in many cases, we can show that sort of sums over different permutations will yield terms that look like this, where we have a dimension, k factorial, and a combinatorial expression. And these are of order k squared over the system dimension. So this shows the spectral gap essentially saying that when you convert this qudit number to dimensions, you're going to get the 1 over dimension dependence. And here's where the k in the numerator comes from. So an idea that has been around for a little while is that if you're willing to pay a dimension factor, you can often convert different notions of distance. And the spectral gap is one of them. The relative error is a much stronger one, but if you want to convert spectral gap to relative error bounds, you can do so if you're willing to pay this factor, which is basically the dimension of the k-fold space squared. We recall, though, that by Schur's lemma, all of the operators commuting with the unitary group have a particular form with a very high multiplicity. And this multiplicity, which is equivalent to sort of a completely mixed subsystem, being part of the state, is going to factor out of the norm conversion and cancel out the main dimension. So when we take p parties and have p-fold copies of this unitary invariant space equivalent to the locally twirled outputs, we actually reduce to a space where the dimension conversions of factors only care about k, and again, kind of forgot about the original dimension. Now, if Alice and Bob use respective overlapping twirls, then again, the concurrent paper by the other authors actually shows that you can do even better with the k dependence. Both papers sort of showed that at this stage you could get the m dependence out of the picture. And how do we get from communication to shallow designs? Well, given a line of small designs, one may iteratively merge them into a full design. So you could think about this bottom here of the diagram on the left as sort of each one of these blocks has been locally twirled. And then at each step, we're going to combine neighbors and eventually get a full twirl. On the right here is showing kind of where the crossing twirls would have to land. Note that they are actually still local. And so the optimal strategy uses order log m small blocks and also order log m communication at each boundary. This generalizes to higher dimensional lattices. So here's a 2D picture, again, doing a similar merge scheme. You can describe these recursively using trees. but the trees all kind of flatten out, and it turns out you can do all of the local and crossing twirls in parallel. So if you consider a subregion of one of these lattices, such as here illustrated by the dashed line, then the subregion will have a boundary, and you can kind of see that only the local or crossing twirls that go through the boundary or have the boundary go through them are going to contribute anything to the entanglement generated between this boundary enclosed region and its complement. And indeed, the entanglement entropy generated by this boundary is very nearly proportional to the boundary. So it's what we call in physics an area law, up to some corrections that are logarithmic in the total system size. In fact, I believe there's some arguments in the quantum pseudo-entanglement paper by Aronson and Boland, Pfefferman, and other co-authors that you probably shouldn't be able to reach an exact area law, but this is showing that it's an area law up to small corrections. And so this is showing that the entanglement entropy that you create is going to be way, way less than what might be expected. And also that the communication between the subregion and its complement is potentially low. So in conclusion, unitary K-design ensembles can approximately be constructed on M qudits using bipartite communication, only order 1 in M, and only with order 1 entanglement. The ensembles can be formed on lattices with area law entanglement up to logarithmic corrections. And we also show that then the depth of these schemes can be made logarithmic in M being, again, the number of qudits or qubits involved in the original system before the K fold copying. So thank you for listening.